in class. And um, so the main quantities we'll be working with for the first test is mostly distance, time, mass, speed, and acceleration for the kinematics units. And then the other quantities like force, energy, and power would be used in the later units, for example, in test two. And so these are just some examples of the quantities and their units. So here's our first question, and I'll read it out loud and I'll give everyone a minute to kind of go over it and think about it, and then we can discuss the answer together. So if a football field is 115 yards and 1 yard equals 0.9144 meters, how many meters long is a football field? And I'll give everyone a minute. So here's the answer. When converting between units, always try to write the conversion as a fraction. So in this case, because the question gave us the information that 1 yard is equal to 0.9144 meters, and we want our final answers to be in meters, we can put the 1 yard in the denominator and then put the 0.9144 meters at the top, because that's what we want our final answer to be in. And then using that, we can multiply it with the given yards in the equation, and that way we can cross out the yard units. And then our final answer will be 105.156 meters. And so next we'll be covering dimensional analysis. And here are some of the common dimensions that you might see in physics. They refer to a basic type of quantity or just a measure of a physical variable without the units involved. So for example, if we're referring to the dimensions of an area, we would say length squared, but the actual units would be whatever is given in the question, so meters squared or centimeters squared. And so these are just some examples of common dimensions you might see. And so here we have another question related to dimensional analysis. So in this question, it's asking us to determine if it's dimensionally correct, given the dimensions for each variable. So using the information given in the questions, we substitute in the dimensions for the variables, and then we check to see if the left side equals the right side. And that way we know that this equation is dimensionally correct. So I'll give you guys another minute to try this problem by yourself, and then we'll take up the answer. So here's the answer to the problem. So for this problem, we just simply have to substitute in the given dimensions and check if the right side equals the left side. So after substituting in the dimensions, we can pick which side we want to simplify. Based on this problem, we can see that the left side, after substituting in the dimension for the variable t, we can see that the left side is already simplified. There's just only one dimension there. And so we can work on the right side, which is more complex, and simplify it. So after substituting into the dimensions into the right side variables, um, we can see that there is a square root, and the square root also means that we can just multiply it by the power of 1/2. And then after doing that, we can do the division of the dimensions inside the bracket. And then after simplifying it, we can see that the two sides equal each other, so the left side equals the right side, in that the two dimensions that are left over are t, which means time. And so this is how we would check to see if this equation is dimensionally correct, by just substituting in the given dimensions in this problem. Does anyone have any questions about this solution? Okay. If not, we can move on to the next topic, which is proportionality. And so proportionality essentially means that two values will depend on each other. So if one variable changes, the other will have to change by a certain fixed amount. And when this happens, these variables are said to be proportional to each other. And this describes many trends and relationships that we see. So for example, if we know that x is proportional to y, we know that when x doubles, y will also double. Likewise, if we reduce x by a half, we know that y will also reduce by a half. And so one of the common equations that we see that depict proportionality is the slope equation, y equals mx plus b. And in this equation, we know that y is proportional to x, as it is dependent on the changes in the x value. So here's another question that we have, and I'll read it out loud. So using this formula and the graph shown below, which relationship would sufficiently describe the relationship on the graph? So I'll give you guys a minute to think about the answer to this question, and then we can take it up together. So here's the answer to this question. The answer is option D, where k cubed is k cubed versus h is the answer. And so when solving this question, we can ignore constants like the number 4 here, because they will always be held constant and they do not affect the changing relationship between the variables. And since we can see that this is a directly proportional relationship given by the graph. As it is linear, we can assume that is similar to the slope equation, just without the y-intercept. So the y equals mx part, or y equals kx. In that case, the proportionality constant. So we can kind of mimic that relationship by bringing k cubed to the other side of the equation by multiplying it, and then in doing so, we will result in a linear relationship where k cubed will equal 4h. And then in this case, to give that linear relationship, j will be held constant. And I know this is something that is similar to the iClickers, except we didn't have that written here. But usually in the iClickers, I know that they specify that a certain variable will be held constant, and so that's the case here. And then, as I said before, we can ignore 4. And when you have a linear relationship like in this graph, you're essentially just looking for two variables in the given equation that will equal each other, and this will give you that linear relationship. Does anyone have any questions regarding this problem? Okay, Krishi, sounds good. We'll just move on to the next topic then, which is geometric proportionalities. So in class, you might have learned that isometric equals the same geometry, but just a different size. And so you might have used that idea to kind of cover topics or problems regarding the heat generated or the heat lost, which we've specified here. And then there's also the area and volume proportionality. So as we're kind of familiar with, area is proportional to length squared, volume is proportional to length cubed, and then mass, which is just all the matter that's inside of a certain object, is also proportional to volume, which is proportional to the length cubed. And then there's also the heat generated, which is proportional to length cubed, which we know is proportional to volume. And then heat, because it's the heat lost is proportional to the surface area of a certain object, which is why we use length squared, as it's also proportional to area. So heat generated would be proportional to volume, and then heat loss would be proportional to the area, because it's concerning surface area. So we have another question here that kind of covers over the geometric proportionalities that we covered in the last slide. So the solution is given here, but if you guys wanted to take a minute and kind of read over it, that would be fine. And then I'll just kind of read over the question, and then we can take a minute to kind of think about it, and then we can come back and discuss the answer together. So Catherine weighs 50 kilograms and her sister weighs 10 kilograms. Assuming they are isometric to each other, compare the rate of heat loss. So since we know that the mass is proportional to length cubed, which is also proportional to volume, and we're given the mass in the question, we can actually use that ratio of dividing their masses and equate that to the ratio of their lengths cubed. And so in this case, MK stands for Catherine, and then MS stands for her sister. So by finding that ratio of length cubed, we can substitute that into the heat loss equation. So first, we would have to use the given information, which is mass, because we're not given their lengths directly. So using mass, we can substitute that into L cubed. But then, as you notice here, we kind of move the cube to the other side, and now we're raising the other side to the exponent of 1/3. And in doing so, we have isolated the ratio of their lengths. And then now we can substitute that into the equation of the heat lost. So by dividing their masses, which is 5, we can substitute that into the equation by raising it to the power of 1/3, and then raising all of that to the power of 2, and then we will get the answer, which is 2.92. And this answer represents the fact that Catherine will lose heat 2.92 times faster compared to her sister. Does anyone have any questions regarding this solution? Okay, if anyone has any further questions about proportionality or conversions, you guys can always post it in the chat and then we can get back to you. But now we'll be moving on to vectors. And so Naveen, if you want to take it from here.
Yeah, for sure. I'm just gonna try and experiment with this annotating tool. Please let me know if you can see what I'm drawing. If not, that's okay. Do you see a red circle?
Yeah, I can see it.
Yeah, okay. So maybe I'll try to use that if I'm trying to show something. It's just gonna be a little tricky with the mouse. But yeah, so vector addition. So basically, when adding vectors, it's really important to just keep track of what the tip is and what the tail portion of the vector is, because sometimes it can affect your final result, and we don't want that. So for this example, we have a vector A in the blue arrow and a vector B, which is green. So they're in their configurations, they're not directly north or south or whatever. And whatever their magnitude is, it's an arbitrary value. And we can also see here that by adding A and B in that certain order of vectors, it's the same thing as saying vector B plus vector A. So that's just a property that is true for vector addition. So in the bottom here, we can see that the tip portion, which I will try to annotate for vector A, is in the red, and over here we have the tip of the vector. So this point at where they meet is just the tip of one connected to the tail of the other vector, and then we can form the red, which is the resultant, and that would basically be the result of the addition of the vectors. And so to prove that they're both the same, obviously there's no numbers here, but if we were to add B first, so we draw vector B exactly like it is up here, and then we take the tail of vector A and connect it to vector B's tip, we find that the resultant is the same. So that's vector addition. So we can move on. Does anybody have any questions about vector addition? I'm sure you're all pretty proficient with that, but vector addition, subtraction is usually where it starts to get a little trickier in terms of just keeping track of like the negative. So here we have vector A and B again. And so it's important to note that vector A minus B is equal to saying, if we want to reframe it in terms of addition, we can say vector A plus a negative vector B is equal to the subtraction of those two vectors. So how do we create a negative vector? Essentially, it's kind of like a reflection. So if I were to take vector B here and I'm going to try to draw a dotted line. So we want the same magnitude, but we just want the opposite direction. And then we have this vector here. That's what the negative of that vector would be. So it's essentially in the opposite direction, but it's the same size and same thing, tip to tail. So vector A and the negative of vector B, and then we've got the resultant in red. Yeah, so we can go on to the next slide. Okay, so this is something that's quite important in all of physics, just knowing your trigonometry values, and it's helpful definitely to memorize them, but I would say to start off, just try to understand. Physics is heavily based on understanding a concept and being able to apply that for any sort of numbers or any sort of word problem rather than trying to memorize it. So I'm sure you're probably familiar with SOHCAHTOA, an acronym to kind of help remember what sine, cos, and tan are equal to. So for this first box over here, we're trying to find the x component of the force vector. So it's important to kind of take all these numbers and symbols and put them into words. And then the same thing for words. You want to take the words and kind of convert them into numbers. So you understand what you're kind of reading. So I'm gonna highlight or try to circle if I can. Okay, I'll just circle, but so this is the angle in this specific case. And we can see in some of the other questions, they've moved the angle around. So for this one, we want to find the x component relative to this angle. So if you use SOHCAHTOA, this is going to take a while, but essentially cos is equal to the adjacent over the hypotenuse, right? So in this case, for the force vector, the adjacent, sorry, for this angle, what is the adjacent value? The adjacent value is the x component, so that's why we're using cos in this example. So you can kind of rearrange it to depending on what you're trying to find out. So in this case, we want to find what the x component is. Similarly, in this one, I won't go through all of them because they are just sine and cos, but let's try this one. So I'm going to try to go full screen. So, sorry. So for the y component of this angle, we are trying to find the y component of this force vector. So the y component is adjacent in relative to this resultant or this force vector. So it would be cos because cos is adjacent over the hypotenuse. This is the hypotenuse of these two vectors. So yeah, so do you have any questions in terms of any of these six kind of diagrams or like how to interpret them? If not, we can move on to the next slide. And you can always ask in the chat as well. Okay, so this is kind of just putting all of this together. And another important thing, right now we don't have numbers, but once numbers start to add up, it's just important to make sure you know what you're doing each step of the way so that you're not making an error in terms of numbers. So uh so what is f2 x component equal to? It's the same thing, right? The x, a way to remember it is the x component is always, or almost always, I would say, the cos, and y is sine, just because sine is opposite over hypotenuse. And if it's set up in this way where the resultant is like that, and then x and y component, um, they would turn out to be like that. So same thing for f1. And then we're trying to find the resultant. So the resultant is the vector sum of f of 1, like the x and y components of both f1 and f2. So it's important to break down your vectors in terms of x and y. So always don't try to add an x component with a y component. Just try to keep all the x components on one side and then the y components on the other side. And then you can find the vector addition. And we don't have a slide for this, I think, but I'm sure you're aware that yeah, the tip, like kind of like the tip and tail vector addition. So right now we have it set up like this, where the resultant is r, and it's going through, this is also a calculus and vectors concept, but like this is the resultant. But if you were to take these vectors and just kind of slightly rearrange the orientation, same magnitude, same vectors, you would still have the same resultant. It's just, it would kind of look different. So that's another way of putting it. And so the resultant in this case is, this might be familiar, the Pythagorean theorem. And it's the square root, because it's a squared plus b squared equals c squared. So the square root of the x component squared and then the y component squared. And then of course, if you have any negatives, so when you're determining your axes, what's their positive and x and y direction, I think that's a really helpful step to start off with. But you're squaring the values, so they would be positive regardless. And then to find the angle, you would use tan, because tan is opposite over adjacent. And so the y value, it would correspond to the opposite value, and x would be adjacent to theta. So does anybody have any questions for this slide? If not, we can move on to the next one. Okay, so significant figures. So just a rule to stick by, addition and subtraction. We want to use the number of decimal places that is the least reliable, because we want to, essentially we're trying to be as sure of these values as possible, right? So if we have 0.02 plus 1.2345, we know that this value is 1.2345 for sure, but we don't have as many decimal places for the other value to confirm that it's, like, it could be 0.020001 or something, right? But we're not sure. So our certainty only goes up till the, what would this be? The 10th, 100th decimal value. So we would only keep 2 decimal places. And so it's just important to keep track of the separate rules for addition and subtraction, and the separate ones for multiplication and division. So for multiplication and division, we want to look at the number of significant figures that are least reliable. So there's usually like a chart which kind of goes over like what is a significant figure. I will try to pull that up and post that in the chat. It's a helpful resource, but I'm pretty sure it would have been in lecture as well. So for 2.2 times 1.45, the first value has 2 significant figures, and then the second one has 3 in total. So we're going to go with the smallest number. So we're going to keep our final answer to 2. So even though it might be like 3.21, we're just going to round it to 3.2, because that's the number of the number of significant figures that we want to keep. So we can move on to the next slide. Okay, so now for Fermi estimates. Yeah, these are basically kind of like estimate related questions that are pretty common on the midterms, and I think even on the exam for Physics 1 AO3. And they shouldn't be that intimidating. They're honestly kind of fun to work through. Yeah, and so we'll go through a few right now. Okay, so how many watermelons would it take to completely fill your bedroom? So this seems like a pretty open-ended question, and it might seem like there's no numbers to go off of. But essentially we want to take whatever words are present in the word problem and not get confused with them. We just want to convert that to math, to symbols, to numbers, and we want to ask what the question is asking, right? So in this case, if we try to decipher this, how many watermelons would it take? It doesn't matter that it's watermelons or any other unit. Basically, we want to see how much of something would it take to fill a volume. So essentially, it's a volume problem. And now we're gonna just work through this together. So um, these are questions that we have to ask ourselves, and obviously you would most likely not get this exact same number if you just use different estimates, but we would try to be in the kind of range, right? So we assume that a standard room is 7 by 8 by 7 meters, the length, width, and height, so that's needed to find the volume of the room. And then how big is a watermelon? Because that's what the question is asking. So we're going to assume that they are spherical, so it's helpful to know the volume of a sphere formula. And we're going to estimate that their radius is 15 centimeters. So based on that, we've got numbers. And another helpful tip in physics, for problems that in the beginning, it's helpful to kind of go through questions and try to come to a number, but oftentimes that can take up a lot of time. So sometimes it's just beneficial to go through a problem and not really care about the numbers, but focus on the process instead. So in this case, we found the total volume of the room, and how many watermelons would fit would just be the volume divided by the volume of a singular watermelon. So based on this, we would have approximately 27, almost 28,000 watermelons. Does anybody have any questions for that question? The Fermi estimate? Okay, we'll move on to the next slide. So kinematics. Okay, so kinematics essentially is just studying movement, right? Like motion. So we'll go through some of the terminology now. I think this is really important that you have a really great understanding of what each term means. So it's important to understand the meaning of the term rather than trying to memorize what it means. So kind of putting it into context, like I usually try to associate an example. So for position, position is where a certain object is in space. So it's in reference to something, or like yeah. And then displacement is different from distance. So this is a really important distinguishing factor. Displacement, we'll go through another example on the next slide, I believe, but it's basically asking how far an object has moved relative to where it was before. So the notation also is very important. Sorry, for position, it's just an X with a vector above it. It's a, and then displacement, there's a delta, that X with a vector. So this is the final position minus the initial position. So there, all of these terms are really interconnected. So, and they're easy to kind of confuse. So it's important to have a firm understanding of what each one means. So for velocity, and velocity now builds up on displacement. So velocity is how quickly does the displacement occur? Or another way of saying this is what is the rate of change of the velocity over a certain period of time? So velocity is a vector, and displacement would be in the numerator then, and time would be change in time, sorry. That's an important, It's change in time in the denominator. And then acceleration is essentially asking, is the object getting faster or slower? So acceleration is related to the change in velocity over a certain period of time. And it can also be expressed as the final velocity minus the initial velocity. And then the change in time is the final minus the initial time. So displacement versus distance. Here's one example of displacement versus distance, and you can essentially see that if a person started off at this point and they were walking and they went all around this entire long-winded route and ended up here, that purple dotted line or curve, sorry, is their distance, and the green dotted arrow is their displacement. So essentially, I like to think of it as a racetrack or like a circular track. So when would displacement or distance have different values? Because sometimes they can be the same. So if you have a circular track and you want to run around the track, you start off at this position and you complete one entire lap. What do you think your displacement would be? If you can type in the chat. Any ideas? If not, it's okay. Zero. Yeah, perfect. So the first time I learned this, I thought it was kind of intriguing that your displacement would actually be 0 meters because you haven't been displaced. Like you ended off where you started off, right? So, but your distance would be whatever, like 400 meters. Um, so the distance is how much you've traveled, and displacement puts it into context or reference to where you started off. So yeah, displacement, sorry, is always smaller or equal to the distance. So we can move on to the next slide.
I'm sorry to interrupt, but Kushi asked a question about the significant figure rule for squaring or square root. And correct me if I'm wrong, Naveen, but I believe that if you are squaring something, it would be the same rules as multiplication and division because, for example, if you have 4 squared, you would just be doing 4 times 4. So I
Yes,
think that those rules still apply.
yes, the rules do apply. I will also just try to, it's also, yeah, for sure, the rules apply, and then just knowing what is considered a significant figure as well. I'll post that afterwards in the chat, because sometimes there's some questions that are a little tricky, and there might be like zeros in between or something, right? So yeah, those rules would apply.
I'll just move on to the next slide.
Okay, so similar to distance versus displacement, we've got velocity versus speed. So velocity is a vector, whereas speed is a scalar. So scalars only look at the magnitude. They don't really care about which direction you're going at or going in, whereas vectors do. So it's magnitude and direction. That's just key to remember. So for example, you have a car moving 25 meters per second. But in which direction? If you include north, so usually the notation would be like 25 meters per second, and then in brackets n for north. And then that you would know that that's velocity, and then speed is just 25 meters per second. Could be in any direction. We just don't have that information. We can go to the next slide. Okay, graphs of motion. So starting off with the position versus time graphs, we're gonna go through each of these and kind of see what each of them means, instead of trying to memorize like, oh, this graph is always equal to this. So for position time graphs, you have the position on the y-axis and time on the x-axis. So what is your position at time 0? in this graph, it's already a certain distance away. Let's say this is 5 meters from the starting point, and it stays at 5 meters over whatever the time may be, whether it's 10 seconds or whatever. So yeah, I'll just go through. I don't know if okay, so I'll go through what we can learn from this graph. So since the slope of this graph, sorry, if we could just go
Sorry.
back.
Yeah, I can go back.
Okay, thank you. So from this graph, we can see that the slope is not changing, right? Because the position is constant at 5 meters for the entirety of the time period. So the slope is 0, or the rate of change is 0. So for slope, it's usually indicated by m is equal to rise over run, or delta y over delta x, or y2 minus y1 over x2 minus x1. So whatever works best for you. But just remember that we can, so if we're given a position time graph, we can extract more information out of it, right? That's what we're trying to get at here. So if the velocity of an object is 0, what is velocity equal to, right? So if we just see this graph and try to think, oh, velocity is 0, it's kind of hard to make that jump. But if you go backwards and you think, okay, what is velocity? It's the displacement over time, right? So is this object being displaced? Well, it doesn't look like it's being displaced because the position is at a constant value, right? So because it's at a constant value, but time is changing, obviously, time is increasing in the x-axis, this object is at rest. So it's not being displaced. And we know that for velocity to equal 0, the numerator would have to equal 0. And for a real value, the denominator cannot equal 0. So now in this second scenario, we have an object starting from the starting point, and over time, it is getting further away from where it started. So this would be a positive slope, obviously. And we can assign random numbers. So let's say this is 0, and this is 10, or 7 actually, and this is 5. So now if we try to find the slope, the rise over the run, so this has gone over 7. The position has gone up to 7 over 5. So delta y, the change in the y value, would be 7. And then the change in the x value is 5. So 7 divided by 5 is a positive number, but it's a constant, it's like a number, right? So it's a constant slope is basically what we're trying to get at. And then similarly for this one, this is just a negative slope. So velocity is constant. So the object is moving at the rate of change is constant over time. Now for this one, the position, this is kind of parabolic, right? So the slope is a curve, and velocity is not constant in this case, because at each point, the slope would be like the instantaneous rate of change of the slope, the tangent would be different, right? So in this case, it is increasing upwards. It's a positive, the object is accelerating because it's gaining, I know this is incorrect terminology, but it seems to be gaining momentum over time. So yeah, any questions about this? This is usually kind of a tricky concept in the beginning for physics. So it's just helpful to draw out the graphs and kind of think about them, but we'll go through some more examples as well. And also we have here that the steeper the slope, the higher the velocity, and we can kind of see this if we try. Something I recommend is if you're not sure of something in physics, draw it out, put in numbers, arbitrary numbers, to kind of figure it out. That's really helpful for physics 1A03 midterms. So if I try to draw a slope here, it looks to be, that's not very accurate, but it looks to be very steep compared to somewhere like here, right? So we can see that the speed or the velocity is getting faster. So yeah, so from the position time graph, we can we can get more information about the velocity over that certain period of time. And we'll move on to the next slide now. Okay, so this is a bunch of position time graphs and their slopes, their interpretation, and what the actual movement may mean based on what we see. So I'm just gonna go over 3 graphs that my physics teacher like gave a helpful hint to kind of remember. So I'm gonna focus on these 3, the curves. And if this is helpful, you can keep it in mind. If not, it might sound funny. But for this graph, we see here that the acceleration is positive. And if you're ever short on time, a funny way to remember this is that it kind of looks like half of a smile. And so a smile has a positive connotation, and this one, the second one, has a negative acceleration. Obviously, try to understand what each graph is indicating, and we're going to go through that as well. But this looks like half of a frown or an upside down U. So it has a negative connotation. And same thing here, it's the other side of the frown. So negative, negative, and positive. And another way that if you ever have to convert kind of from like an acceleration, velocity, or position time graph, which I'll go over as well, but if there's a smile that's positive, people are happy. And so when are people happy? When money is increasing. So this is a position time graph, but if it were an acceleration or velocity time graph, we would have an upwards, an increased slope. So yeah, so I'll go over that for I believe a few slides later. But does anybody have any questions so far or for any of these graphs? If not, we can go to the next slide. Okay, so this, honestly, I find this to be kind of fun, kind of converting between graphs. So for the velocity time graph, we have 3 different components here. And I like to divide it up. So the first section here, oh, that's not very straight. The first section here is a constant velocity. The second portion is speeding up. The third, and you can number these as well, is same constant velocity, but it's a different higher value of a constant velocity. And the last segment is slowing down. So constant velocity, the slope is 0, and we could convert to the position time graph. So just based on this first segment, so I'm going to number this 1. What do you think this portion of the position time graph would look like? Like, would it be a curve? Would it be a straight line? Would it be a positive, negative slope? What do you think? If you could type in the chat. Straight line with a positive slope. Yeah, perfect. So sometimes these concepts aren't very intuitive. But yeah, it would be a straight linear positive slope. And if this graph were to be extended and we had a negative constant velocity, it would indicate that we had a negative but linear position time graph for that portion. So this is just something to keep in mind. And then for the second portion, we see that the velocity is increasing over the period of time. So if we were to convert this to an acceleration time graph, it would be a constant acceleration because the slope for this, let's say the slope is 5 meters per second squared. And another helpful exercise is the units, right? So what is the slope? Delta y over delta x. So we're just going to look at the units. Meters per second is the y unit, and the x is seconds. So you're dividing the reciprocal, and it would be meters over seconds. Maybe you guys are faster than me, but this is how I work through division, divided by seconds. So it's s over 1, and then you're gonna flip or use the reciprocal. So obviously when you practice, you'll this will become intuitive, but this is how we get the acceleration units. So I think it's helpful to kind of derive equations and units as well. It just gives you a better sense of where these symbols and variables are coming from. So that is the unit of acceleration. So therefore, when we take the slope of the velocity, we get the acceleration. And here in the third segment, we just have a constant velocity, but it's a higher velocity. So a higher velocity means that the object covered a greater displacement for that portion of time. And then when it's slowing down, same thing, it's just a negative slope. So the change in velocity over that time would be negative. So a negative velocity could indicate that the object is moving in the negative direction. A negative velocity could also, so when we're trying to create an acceleration time graph, it would be a negative like slope. And yeah, so any questions about that? Okay, if not, we can move on to the next slide. Okay, so this is how I like to tackle these questions. I try to kind of draw out whichever graph I'm given and draw 3 lines like this and say I have the position time graph, or actually say this is the velocity time graph. I'm going to try and create the acceleration time graph and the position time graph from this graph. And essentially this is what these 3 rows are trying to achieve as well. But it's just that when you line them up in this way, it's easier to see what is happening for each segment, and then you can kind of split it up like that to figure out what's going on in each portion. So for the first one, we have a stationary object. The position has not changed for that set period of time. And we know that the slope of the position time graph is the velocity. So it's going to be a 0 velocity. And then acceleration is the change in velocity. And since the velocity has not changed, the acceleration is also 0 meters per second squared. For uniform motion, we've got a positive linear slope. Let's say it's a slope of 2 meters per second. So the velocity is 2 meters per second for the entire duration. There's no change in the slope. And the acceleration is the slope of the velocity time graph. So there's no, the slope is 0, so acceleration is 0. So now we've got motion with constant acceleration. So the acceleration is constant, but the position change is not. So it's positive, it's half of a smiley face. So it's increasing and it's in the positive direction. So the slope is different for each So we cannot calculate a slope for this entire graph. Each segment of this graph has different instantaneous slopes, right? So we've got the velocity time graph, which is linear and positive, and then the slope of that would also be positive, and so that gives us our constant acceleration. Yeah, so any questions about that? And if you have any specific like questions as well, we can go over those shortly as well. If not, we can go to the next slide. Okay, so these are just some extra practice. It's the same concept, just trying to really understand what each graph is saying. I'm not going to go through all of these because I think that would be quite redundant, but does anyone have any questions about a particular graph from here and trying to interpret what it means? If not, we can move on to the next slide.
So the last section we'll be covering in this review session will be related to kinematic problems and the different equations that everyone might have seen in class and that we'll use for these problems. So as I said, that these are some of the equations that we'll use, and if you have no acceleration, you can use the equations that are on the right side. And then we listed here the variables that you would need for every kinematics problem. So acceleration, initial and final velocity, change in position, which is displacement, and then change in time. And so if you're solving for one of these, you would have to use one of these kinematic equations. So to start, this is our first question. And I'll read it out loud, and then I'll give everyone a minute to think about it and try and get an answer, and then we'll take up the answer together. A plane has a takeoff speed of 88.3 meters per second and requires 1,365 meters to reach that speed. Determine the acceleration of the plane and the time required to reach the speed. So I'll give everyone a minute. Okay, and now we'll take up the answer. So in this question, we were given the information that the initial velocity is 0 meters per second. The final velocity is 88.3 meters per second, which is the takeoff speed. And then the distance or the change in position that we have is 1,365 meters. And then we have to find the acceleration as well as the change in time. So to find the acceleration, we can use the kinematic equation, which doesn't involve time, which would be final velocity squared equals initial velocity squared plus 2 times acceleration times change in position. And so plugging all our given information in, we can solve for acceleration. And then our final answer for acceleration will be 2.86 meters per second squared. And then using that value, we can use the other kinematic equation, which does involve time, and substitute in the final velocity, initial velocity, as well as the acceleration that we just found from the first equation into this different kinematic equation to solve for time. And so plugging everything in and then calculating it will yield a result of 30.8 seconds. And so that will be the change in time. And so those are the two final answers that we get for this question. Does anyone have any questions about the solution? If not, we can move on to the second question. So in this question, a kangaroo is capable of jumping to a height of 2.62 meters. And they're asking you to determine the takeoff speed of the kangaroo. So I'll give you guys another minute to try this problem, and then we can discuss the answer after. So this is the solution to the second question. So just based on the information given in the question, we can determine that the acceleration will be negative 9.8 meters per second squared because the kangaroo is in the air, and therefore the force that would be affecting it would be gravity, and that's why we are using negative 9.8 meters per second squared as our acceleration. We know that the final velocity would be 0 meters per second, and the displacement would be 2.62 meters. And then we are asked to find the takeoff speed of the kangaroo, which is the initial velocity. And I just want to note that because the kangaroo reached its max height, which is the peak of its jump, you would say, its speed at that peak would be 0 because it's not moving at that at the maximum height that it reached. So that's why we say that the final velocity is 0 meters per second. And so just substituting all that given information into our equation, we can solve for the initial velocity. And once we plug that information in and calculate it, we will get an answer of 7.17 meters per second. Does anyone have any questions about this solution? Okay, and then we can move on to our last question then. So the final question, I'll read it out loud. A baseball is thrown straight up into the air and has a hang time of 6.25 seconds. Determine the height to which the ball rises before it reaches its peak. And here's a hint. The time to rise to the peak is 1/2 of the total hang time. So I'll let you guys try it for a minute and then we can take up the answer together. So here's the solution to the third kinematics question. So we can use the given information to solve this question. So from the question itself, we can retrieve that acceleration will be again negative 9.8 meters per second squared because it is a projectile motion question and this ball is thrown in the air. And then final velocity, again, similar to the last question, it will be 0 meters per second at its maximum height. And then the total time is the half time from the total given time is 3.13 seconds. And so we have to use the half time because if we're using the full time, then we won't get the correct answer because we're just trying to find the vertical height that the ball traveled to reach its maximum height, and it reaches its maximum height at 3.13 seconds. So that's why we are only using the half of the total hang time. And so first we would have to use the equation with final velocity equals initial velocity plus acceleration times time, and then that would give us our initial velocity. And then we plug that into the second equation, which is final velocity squared equals initial velocity squared plus 2 times acceleration times change in position. And then because we had to find that initial velocity first, now using this second equation, we can actually solve for the height that the ball was thrown to. And so plugging everything in, plus the initial velocity that we found in the previous equation, we will get an answer of 48 meters. And that's how high the ball traveled. So does anyone have any questions about this solution? So if not, you guys can continue to ask questions in the chat about any of the earlier topics that we covered or about kinematics. And I believe that Navreen, that you want to go over an example, so I can share that example on the screen.
Yeah, that would be great. There was a great question in the chat. I'm not entirely sure if it's beyond the scope of this midterm. You guys will probably be able to confirm, but I can take a look at the course outline as well. But it's definitely an applicable question, and it just kind of takes our understanding and to the next kind of level.
Yeah, so can everyone see my screen with
So
the image?
I see the presentation right now.
Okay, I think I have to stop sharing this presentation and
Okay,
then I'll share the image.
sure, yeah. Okay, perfect. Thank you so much. So this is just an example that I found online that kind of depicts how the position, velocity, and acceleration time graphs would look in a case where the velocity graph is kind of, parabolic, right? It has the smile or the frown. So here we're going to start with a velocity time graph. And for this segment, basically where this line is drawn, it is, well, the entire segment looks like a frown, right? But it's kind of split into two. So this one is the velocity is increasing and then it starts to kind of plateau a little bit. And at this point, the slope is 0. So that's helpful in certain questions. And then here it's level, and then now after some time, it starts to increase. So basically for the position time graphs, another key to distinguishing if it's a frown, this is not a great benchmark to use. Just make sure you practice and like confirm you're using it correctly. Because this portion, if continued, looks like a smile, right? This portion, the beginning portion. But once we reach, this is kind of like an inflection point, because this portion, that's terrible, but that second portion is starting to look like a frown, right? So that's kind of what the position time graph would look. And obviously the acceleration is just negative because it's a frown, we're losing money, we're sad. And the position time graph has two components to it. So the degree, this is, I think, bringing us back to like calculus, but it changes, right? It changes from a smile to a frown, right? So for this first half of the segment, what does that mean? So in the velocity time graph, we saw that it was changing velocity quite fast, and then it started to slow down. So this is kind of, we can think of like throwing an object up in the sky, right? And then gravity, the effects of gravity. So this is usually in kinematics questions. So the object starts to slow after a certain point, and now it's changing direction, right? Because it's falling down. So if we were to label this as the positive y direction and this as the positive x, then the object is first moving upwards in the positive y direction, and now it's going towards the ground, right? So it's becoming negative. So for this first half up until here, at this time point, the position is, it's not constant, it's not a constant slope, but it's increasing. And then for this second portion, it's also increasing, but now the position is starting, well, at this point, once it's hit the ground, the position won't change, right? So it's starting to plateau. But this is just really important to notice that this is an inflection point. So although for this entire segment from here to here, it's a positive slope, it looks like it could even be linear. It's important to notice that you kind of have to continue the graph. So this does require a little bit of thinking about, is this a smile, is this a frown? So I would not recommend to use this tool if you're not really comfortable with it. Stick to what you kind of follow, and then you can test this out, like if it works for you. But yeah, so does anybody have any questions about that? If you have any other questions from, no worries, Midaha. If you have any other questions as well from any past midterm practice, lecture, anything like that, I'm not sure if the chat feature is allowing us to upload images, but you can maybe share your screen if we can give you that permission, or your whiteboard, because I had some difficulty trying to upload the image as well. I'm gonna try to see if I can edit a setting so that you can upload images. Okay, I think you should have the ability to share like your whiteboard. But if not, let us know if we can try to find a question from our end. Yeah, feel free to ask any questions. Type them in the chat. They don't have to be specific questions as well. Sometimes it's just a matter of understanding really what a concept, a term really means. And yeah.
So we'll be on call for a few more minutes if you guys want to share any questions that you have. If not, you're free to leave if you don't have any questions. Thank you for joining this Physics 1AO3 review session. Yeah, so we'll be online for a few more minutes if anyone has any questions.
No worries, Kushi. I'm glad that it was helpful. I'm sure that physics can be really intimidating, but it's honestly really fun once it kind of starts to make sense. And yeah, just I would highly recommend doing as many practice questions as you can, going to office hours, and using the resources available. And maybe you'll end up really enjoying the course as well. So yeah. Okay, question 15 from midterm 1, version 1. Let me see if I can access it. Midah, if not, do you have the ability to share your screen, perhaps, to show the question? Yeah, okay, so maybe do you want to try sharing your screen? Um, just to save some time. Okay, perfect. Um, so I'm just gonna read the question and then I'll let you know what I interpret from it. Okay, I'm just gonna talk through the question, and Esvenia, if you want to join in as well. Um, so for physics questions, I try to read the question and come up with an answer myself before looking at the answer choices. I find that's a helpful technique for me. But sometimes it's not really possible. So in this case, we kind of have to look at all the statements and evaluate if each one is correct, and if we can eliminate one right off the bat. So this is the velocity time graph. Physics girl travels a greater distance and Einstein travels a greater displacement. So we do know that from the velocity time graph, well, from a velocity time graph, the slope of a position time graph is the velocity, right? So um distance and displacement. I have to confirm, but I believe the area under the graph is the displacement.
Yeah, that's right.
Yeah, okay.
Yeah.
So if the area under the graph is displacement, oh yeah, and so physics girl is moving in half of hers is in the negative direction, right? So it would cancel out, right?
Yes, that's right.
Yeah. So it looks like physics girl's displacement would be close to 0 and Einstein would have a greater displacement. So that part looks correct. So from that, we can eliminate B. The physics girl does not travel a greater displacement. So physics girl travels a greater displacement and distance. So we said that she does not travel a greater displacement, so then C is eliminated. Einstein travels a greater displacement. That could be true. We have to confirm the distance, and both of them travel the same distance and displacement. So we know that E is not accurate because they don't travel the same distance and displacement. So now we just got to evaluate the distance. So from a velocity time graph, how do we figure out the distance? Velocity is displacement over time. We have to figure out the position time graph, right? So we have to work backwards. So I'm just going to try to draw that out. So for physics girl, it's a negative linear slope. So a frown. And for Einstein, it would have two inflection points. So physics girl, they both have the same time value. A greater distance. Let me just confirm.
I think that when doing displacement, how we kind of like canceled out the area that physics girl traveled like under the graph based on the positive and negative areas, and how we kind of reached that conclusion that Einstein traveled a
Yeah.
greater distance. So if we don't subtract them, that would account for distance, I believe, and not displacement, because displacement would be the change in position.
Yes.
So just based on that, I believe that physics girl would travel a greater distance while Einstein would travel a greater displacement.
Yes, because distance is. So for distance, we kind of have to break it up into the portions, right?
Mhm.
Um, so there aren't any numbers given here. But the distance for the first portion is like the area is greater for physics girl. Yeah,
Yeah.
I believe that would be correct. And then even though it goes negative, it's still a larger area, so it's a greater distance. And since distance is, sorry, displacement is a vector, we're not looking at the positives and negatives. So based on that, it would be A, right? Based on that reasoning, that physics girl travels a greater distance and Einstein travels a greater displacement. Is that correct, Medea? Yes? Okay. So I hope that reasoning made sense. It took us a while to get to it too. Because yeah, so distance is from
Yeah,
the, yeah,
sorry, do you want to answer?
no, you can go ahead.
Okay, when going from velocity, so we know that going from position time graph to velocity is taking the slope, but going backwards from velocity to position time graph would be the area under the graph. And so what we did for this question was, for displacement, we subtracted the positive area from negative area, but if we're just finding distance overall, we would just add all of the area under the graph.
Yeah, I'm gonna try to find a link to kind of show what we're talking about. Um,
I did find one with values.
Yeah,
If I could, I'll share it.
yeah.
So this is an example that I found online and just kind of goes over how we were discussing earlier about the difference between distance and displacement when analyzing the velocity time graph. So here they actually gave us values. So for distance, we would add all the areas on the graph, including that negative um, or the red region that they have here on the graph. But then for displacement, you would have to subtract that negative area.
Yeah, so it's really similar concepts, but it's just the subtracting or the negative area. Yeah. Do you have any other questions? Yeah, for sure. If you want to share your screen again. Question 16. Yep, okay. So balloon is rising straight upward at constant speed of 6 meters per second. So constant speed means that the slope is 0. So it's not accelerating. Acceleration is equal to 0. So we can take that piece of information and jot that down in case we have to use like a kinematics equation. So I just like write down acceleration equals 0 meters per second. V equals 6 meters per second. When the balloon is 12 meters above the ground, a gun, okay, so it's already rising straight upwards. So the velocity is upwards. When the balloon is 12 meters above the ground, a gun aimed at the balloon fires a bullet straight upward from ground level with initial speed. So V initial equals 30 meters per second. While traveling upwards, the bullet hits and pops the balloon. How far above the ground? Okay, so this is a really long-winded, elaborate, and wordy question. But I'm just gonna try to kind of like make a diagram and then go from there. So how far above the ground was it when the bullet, how far above the ground was the bullet when it popped the balloon? So we're trying to find the y, like the height. So that's our variable. So I'm assuming that when the bullet is fired, the balloon is still rising upward. It's not stationary at 12 meters, so it's moving 6 meters per second during that. So from that time point. Um, so how far above the ground was that? So it's kind of like a point of intersection question, right, Esvanya?
Yeah, so I think I remember actually doing this question, but
Really?
so I'm going to try and solve it again.
Yeah.
Yeah.
Okay, so basically, from what I remember, point of intersection, you're gonna make two equations and you're gonna find when the end point, like the height is gonna be the same for both the values, right? When they intersect. So the delta x, but in this case it's delta y, right? And we're just gonna set them equal to each other. So I'm just gonna try to set up the equation. Okay, so what do we know? We don't really have any time given. They're not asking for the time as well. But we do know the initial velocity. We know the velocity of the balloon and the bullet. We know that it's not that the balloon is not accelerating, so we can cancel out any a value if that's present in the equation. And we know that the balloon started at a position that was already 12 meters above the ground, but I don't think we're gonna need that in the equation. So which formula? And we're trying to solve for delta y. So I think we could use the equation delta y is v plus I. Would the final velocity, so okay, the bullet is fired straight upward. So when does it catch up to that basically? So the distance, velocity equals distance over time. Okay, and you also have to accommodate for the fact that they're not starting at the same position. So they're moving at okay. So the end distance traveled by the balloon, let's say that's x. We don't know what that value is. Or actually, sorry, let's just keep that y. And y is equal to x plus 12. So 12 meters is the height of the balloon when it started off, and then it travels x some additional distance. And y in its entirety is the distance traveled by the bullet. So both the y value is the same for both of them. It's just that balloon started 12 meters higher up. So we're gonna try to represent y for the bullet and a balloon separately and then put them together. So for the bullet, delta y is equal to the initial velocity. Espania, which equation are you leaning towards?
Um,
Because if we use the like delta x is equal to v initial t plus half at squared, right? We can
Mhm.
cancel out the acceleration because it's not accelerating. But we have another variable time, right?
Yeah. Um,
How come there's no gravity acting on it? Like on the bullet?
oh, there would be. So
There
the
would be.
acceleration for the bullet would be negative 9.8.
So gravity is acting on both the bullet and the balloon? Or just on the bullet?
I don't because it says there's a constant speed, so I think
Yeah,
acceleration is just 0.
true. So that becomes minus 4.9 delta t squared. So then this is a quadratic equation. We got to solve for t. So right now what I have for the Blitz equation, I have delta y is equal to 30 delta t. And for the balloon, I have delta y is equal to 6 delta t minus 4.9 delta t squared plus 12. That's going to do how the same.
I'm sorry, could you write that out because I didn't, or could you just repeat it?
Sure. So for the bullet, I have delta. So basically, how I represented the total distance is y, whenever they meet the point of intersection. So from the ground to the intersection, and that's equal to x plus 12. So for the bullet, it would be delta y, because it starts from ground, is 30 times delta t, if we're saying acceleration is 0, right? And for the balloon, delta y is equal to 6 delta t, because the velocity is 6 minus 4.9 delta t squared plus 12, because we want to add the 12 meters that it was higher up.
Yeah, I do have the same equation.
Okay, so now we can say that 30 delta t, sorry, Madaha, are you following, or would you like me to try and write this down?
Um, if you could write it in chat, that would be really helpful.
Okay, sure. I will type it up then. Um, so this is what I have right now. 30t is equal to 6t minus 4.9t squared plus 12. And so our expression is y is equal to x plus 12, where x is the additional distance traveled by the balloon, and y is total point of intersection distance. So when we rearrange this to one side, we'll get minus 4.9 delta t squared, 6t minus 30, so minus 24 delta t plus 12 is equal to 0. So I'm just going to plug this into the quadratic equation and see what we get. Okay. So it comes out to be 0.5 and negative 5.35. Okay, so the negative value is irrelevant, so delta t 0.5. If we plug that in to delta y, 30 times 0.5, we would get 15. And if we plug that into the other one, 6 times 0.5, 0.5 squared plus 12. Let me just check. Sorry, I think it's slightly off. It's not 0.5, it's 0 point something something. Okay, so 0.457. Okay, so based on this calculation, I get 13.71. The closest answer is 13.1. Okay, so it's wrong. So let's see where we went wrong. Espenia, did you get a different result?
I'm still calculating it,
Okay.
but um uh okay, I kind of have a different equation, but I'll just try it out and
Sure.
see if it works, and then I'll um write it in the chat.
Okay. Oh wait, sorry, I think I inputted the wrong quadratic equation. So my no, it's a calculation error. Okay, so I think we had the right idea and equation and everything. It was just a calculation error. So the equation how I sent in the chat and set up was fine. So it would turn out to be 4.9 t squared after just rearranging it minus 24t plus 12 is equal to 0. And then when you use the quadratic equation, the value of t, the positive value, comes out to be 0.5653. So now when you plug that into the original equation, the height will be equal to 12 plus 6 multiplied by 0.5653. And that turns out to be 15.4 meters. So we were on the right track, had everything. It was just a calculation error, and that's quite common, especially with the quadratic equation. But does that kind of reasoning make sense? Like how we got those equations?
Yeah, I get it.
Yeah? Okay. Perfect.
Thank you.
No worries.
Yeah, I also got the same thing. I think I was using the wrong mode for the quadratic equation and I just
Maybe,
figured it out.
yeah, that might be the
Uh,
case. Yeah,
I haven't used it since first year. So
same. It's been a
yeah.
while. Yeah.
Thank you. Bye.
No worries. Good luck on your midterm.
Good luck.